Welcome viewers. This lecture is in continuation to my earlier lecture on eigenvalues and eigenvectors. In this lecture we will be discussing eigenvalues and eigenvectors of some special matrices, and we will be discussing similar matrices. I assume that viewers have already gone through my first lecture on eigenvalues and eigenvectors and characteristic equation. We start with eigenvalues of some special matrices. We have already been discussing matrices which are real matrices, that means the elements of the matrices are real numbers. However, in many situations the elements may be complex numbers and we say the matrices are complex matrices. Let us consider a vector V in Rn consisting of components x1, x2, xn. So, V is equal to x1, x2, xn, its transpose is a vector in Rn. Then the length of the vector V is defined as x1 square plus x2 square plus xn square. Now, length, as we all know, is a positive number and it is 0 only when the individual components x1, x2, xn are 0. So, you can verify this: when x1, x2, xn are 0, then the length of V is 0, and we define length of V as V transpose V, which is the vector x1, x2, xn, the row vector, multiplied by the column vector x1, x2, xn transpose. This is also denoted by inner product of x and x. If we extend this concept to complex numbers and let us apply it to a complex vector 1 comma I transpose, then one can notice that its length will be 0. So, this vector is not 0 vector, but its length is 0 if we apply this definition of length which we have already developed for real matrices. So, we need to redefine this length in the relation to complex matrices. So, let us redefine it, that length V square is equal to V conjugate transpose times V. V conjugate transpose means we first take the conjugate of the numbers. These numbers are complex numbers, so conjugate means they are complex conjugates, and then multiplied by the vector x1, x2, xn transpose. And if you perform this multiplication, then this comes out to be x1 bar x1 plus x2 bar x2 and x1 xn bar xn, and we define it as the inner product of x and x. And if you use this definition, this revised definition for length, then 1 plus I transpose square comes out to be 1 minus I, because minus I is the conjugate of I, multiplied by 1 I its transpose, and if you multiply it, it is 1 and minus I square, which is also 1. So, the length is 2. So, length square is equal to 2, and this is not 0 when this vector is not 0. So, we know that this number is now a real number, and this has to be because length is a positive real number. So, we extend the definition of length in this particular manner, and accordingly the inner product of two vectors x and y is defined as x bar transpose y. One may notice that x bar transpose y is not the same as y bar transpose x. This is in contrast to what we have in real numbers, when length from x to y is the same as from y to x. Similarly, Cx, the length of Cx is equal to C bar x. It is not C, it is C bar. So, if we have a complex number, we have a complex vector, then C of x is C bar x. Of course, when we apply it to a real number and C happens to be real number, then C bar and C are equal. Then we combine the conjugate and transpose, and we write it as star denoting the conjugate transpose, and accordingly we can say that inner product x y is equal to x star y. So with this notation we have introduced x star y as the inner product of x and y. The vectors x and y are orthogonal when x star y is equal to 0. So this is true for, this is the definition we apply for complex vectors x and y. Now let us illustrate these concepts with the help of an example. So find length and inner product of the vector x, which is 1 comma 1 plus I transpose, and y is equal to 1 minus I comma 2 transpose. So length of vector x will be equal to 1 comma 1 plus I square, 1 comma 1 plus I, its length will be equal to under root of this product, and if you work it out, it is 1 into 1 plus 1 minus I into 1 plus I, that gives me under root 3. While the length of the second vector 1 plus I 2 is equal to 1 minus I 2, that is the conjugate of this number, multiplied by 1 plus I 2, and then its transpose. We take the multiplication of these two matrices, in fact these two vectors, and this comes out to be under root 6. And if you want to, if we have to calculate the inner product of x and y, it is defined as x bar transpose y, then x bar transpose is 1 comma 1 minus I, and y is 1 plus I comma 2, that is given to us, and if you multiply, it comes out to be 1 into 1 plus I plus 1 minus I into 2, and that simplifies to 3 minus I. Now this is about vectors. Now we go to a special matrix, is a Hermitian matrix. It happens to be a complex matrix and in fact a square matrix. So we say a complex square matrix A is Hermitian if A is equal to its transposed conjugate. That means A is equal to transposed conjugate. So we have first taken the conjugate and then transpose. In fact, doesn't make much difference whether we first take the transpose or we take the conjugate, and we denote it by A star. So if A is equal to A star, then the matrix which is of complex elements is a Hermitian matrix. Now if we have a square matrix A, then a typical element in this is Aij. Then according to this definition, A is Hermitian if Aij is equal to A bar Ji. This bar denotes the conjugate and this indices denotes that it is being transposed. So Aij is equal to Aj bar. If this condition is satisfied, then the matrix is Hermitian. However, if J is equal to I, then one can notice that Ai is equal to A bar Ii. That means the diagonal elements have the property that the element is equal to its conjugate, and this will happen only when the number is a real number. That means if we have a Hermitian matrix, then diagonal elements will always be real. And from this one can also derive that when A is a real matrix, then A bar is equal to A. The real matrix, so conjugate will be the number itself. So A bar is equal to A. So if you consider this A star, since A bar is equal to A, so this A star will actually reduce to A transpose. So when A happens to be a real matrix, then A is equal to A transpose for matrix to be Hermitian, and this means a real Hermitian matrix is a symmetric matrix. So if the matrix happens to be real matrix, then it is nothing but a symmetric matrix. Let us take an example. We have a complex matrix. The diagonal elements are 1 and 2, and 1 plus I and 1 minus I are non-diagonal elements. So let us calculate its conjugate. So conjugate of 1 is 1, conjugate of 2 is 2, conjugate of 1 plus I is 1 minus I, and conjugate of 1 minus I is 1 plus I. And this means if you take the transpose, then A star is equal to A, because when you take the transpose, then this 1 plus I will go here and this 1 minus I will come here. So this A bar transpose is nothing but A. So this matrix is a Hermitian matrix. Then the result is that x star x is always real, whatever be x. So let us consider x is A plus IB comma C plus ID. So these are complex elements of our 2 by 2 matrix. I proved this result for 2 by 2. In fact, this can be done for nth order vector. So x star x is equal to A minus IB into C minus ID, that is the x star, and this is the column vector. So x star will become the row vector and the corresponding elements will be the conjugate. So A plus IB will become A minus IB and C plus ID will become C minus ID, multiplied by A plus IB and C plus ID transpose, and when you multiply it, it is A minus IB multiplied by A plus IB, that gives me A square plus B square, and the second element here is when multiplied by this gives me C square plus D square. So AB CD being real, because A plus IB and C plus ID being complex, so this is a real number. So x star x is always a real number. Then if A is a Hermitian matrix, then x star Ax is a real number. So this is another result. Let us try to prove this. Let A is a Hermitian matrix, we have to prove that this number is real number. This number is a real number when its conjugate is a real number, and in fact x star Ax is nothing but a 1 by 1 matrix, because x star is a column vector and x is a column vector and x star is a row vector. So this product will be 1 by 1 matrix. So if this is a real number, if its transpose conjugate is a real number, then that means that this is a real number. So to prove x star Ax is equal to x star Ax transpose, so we are proving this result by proving this property, x star Ax is equal to x star Ax star. For this purpose, we will evaluate x star Ax star by this can be evaluated using these properties. We know that AB transpose is equal to B transpose A transpose. That means when you take the transpose of a product, the order will change. So this means AB star is equal to B star A star. Now this result will be using to establish this result. So I start with the right hand side, x star Ax star. So that means this is the first matrix and this is the second matrix. So second matrix will be starred first and this first matrix will be starred next. So it is Ax star multiplied by x star star. Now Ax star, again I am using this property, so it becomes x star A star, and when I take conjugate twice, because conjugate is a operation which will be negated if we do it twice, so x star star will become x, and then this is nothing but x star Ax, because this multiplication is associative, so these brackets doesn't have any meaning. So we have proved that x star Ax star is equal to x star Ax, and this is possible only when this number is a real number. So we have proved that if A is a Hermitian matrix, then x star Ax is real. Now on the basis of this result, we will prove that the eigenvalues of Hermitian matrices are real. So let us see how we prove this result. So let us take lambda as an eigenvalue of Hermitian matrix A. Then we can write Ax is equal to lambda x, x being the eigenvector corresponding to eigenvalue lambda, and A is Hermitian. we pre-multiply this equation by x star. So we'll have x star Ax is equal to lambda x star x. Now we have already proved that left hand side is real number in my earlier result, and also I have proved that x star x is a real number. So left hand side is a real number, right hand side is a real number, so this lambda cannot be complex, because if this is complex then this has to be complex. So lambda is real, and that is how we say that Hermitian matrices will always have real eigenvalues. We illustrate this with an example. So let us consider a matrix A consisting of 0 minus I in the first row, I 0 in the second row. So it's a 2 by 2 Hermitian matrix. So we'll see what are its eigenvalues. To calculate the eigenvalue of this matrix, I have to compute lambda I minus A. So determinant of lambda I minus A equal to 0 is the characteristic equation for this given matrix, and for this lambda I minus A is to be computed. So lambda into I, that is lambda, A is not contributing here in the first element, so it is simply lambda. Then the second is lambda I, so no contribution from I in this element, so it is minus A, so it is I here. Then this I will become minus I, and then we have this lambda. Now if you evaluate this determinant, it is lambda square minus, and this minus will make it plus, so it is plus I square, and plus I square becomes minus 1. So determinant lambda I minus A is lambda square minus 1 equal to 0, and this is a second order equation in lambda which can be easily solved, and we get the eigenvalues of given matrix are real and they are 1 and minus 1. So we have established a result and we have verified this in this example. Now the determinant is product of eigenvalues. This is the result which we have established in earlier lectures. So here we have a Hermitian matrix which has real eigenvalues, and if we combine these two results, we can say that the determinant of Hermitian matrix is real, because all the eigenvalues are real, so their product will also be real, and product of eigenvalues is determinant, so the determinant of Hermitian matrix is real. Now this is an important result. It says that a real symmetric matrix has real eigenvalues. Now this result can easily be derived from what we have done so far. We have Hermitian matrix having real values, and a real Hermitian matrix is real symmetric matrix. So if we use that result, we can easily arrive to the result that a real symmetric matrix has real eigenvalues. However, if you consider this matrix A, it is symmetric because this is a mirror image of this, so it's a symmetric matrix. You can calculate its eigenvalues. Determinant lambda I minus A is equal to lambda, and this also lambda here, it is minus I and minus I simplified, it is lambda square plus 1 equal to 0. Therefore, this characteristic equation lambda square plus 1 equal to 0 gives me eigenvalues as I and minus I, and that means this symmetric matrix gives me eigenvalues as complex numbers I and minus I. Where we have gone wrong, this is a symmetric matrix but not a real symmetric matrix. So the result which we have stated is related to real symmetric matrices, and the result is that a real symmetric matrix has real eigenvalues. The symmetric matrix may have other eigenvalues. Now we come to another concept, skew Hermitian matrix. A complex square matrix A is skew Hermitian if minus A is equal to its transpose conjugate. That means A is equal to minus of A star, and when A is real matrix, then we know A bar is equal to A, and this reduces to A star is equal to A transpose, and that means A is equal to minus A star means minus A transpose. So if we have a real matrix, then it will be skew Hermitian if A is equal to minus A transpose, or we say that a real skew Hermitian matrix is a skew symmetric matrix, because this is the definition of a skew symmetric matrix. So if a matrix is real and it is skew Hermitian, then that matrix is going to be a skew symmetric matrix. We may notice that if A is skew Hermitian, then I times A is Hermitian. Let us take an example. We have been given a matrix A as 0, 1 plus I, minus 1 plus I, 0. Let us see what is its conjugate, A bar. So these diagonal elements will not be affected, but this 1 plus I will become 1 minus I when we take the conjugate, and minus 1 plus I, its conjugate will be minus 1 minus I. So A star will be the transpose of this. So this row becomes this column and this row becomes this column, and from here if you compare A and A star, one may notice that A star is nothing but minus times A. This is 0 and 0 doesn't make much difference, but this element is negative of this and this element is negative of this, and hence A star is equal to minus A, or we can say that this matrix is skew Hermitian matrix. So given this skew Hermitian matrix, we will see that if we multiply this matrix by I, then what we have, a resultant matrix as a Hermitian matrix. So let us do it here. The matrix IA is Hermitian. So we multiply this matrix A by I. Let us call this matrix as B. 0 multiplied by I, this remains as it is. So diagonal elements are not affected, but this element will become minus 1. Why? Because I into I is minus 1 and 1 into I is I, and this element will become minus I, minus 1, and 0 remains as such. So this is B as I times A. We calculate its conjugate. So conjugate of minus 1 plus I is minus 1 minus I, and conjugate of this is minus 1, and this minus I will become plus I. Conjugate means the imaginary part will be negated, and then B star, the transpose conjugate or conjugate transpose, is equal to the transpose of this matrix, that is row becomes column and this row become this column, and from here if you compare B and B star, this is nothing but B is equal to B star, and that proves that B is a Hermitian matrix. So A given to be skew Hermitian, I times A is Hermitian. Then every eigenvalue of skew Hermitian matrix is pure imaginary. We have proved a result related to Hermitian matrix, and we found that Hermitian matrix has real eigenvalues, but if the matrix happens to be skew Hermitian, then its eigenvalues will be pure imaginary. So to prove this, let K is skew Hermitian matrix, then Ik is Hermitian matrix. Like lambda is an eigenvalue of real Hermitian matrix, that is lambda is a real eigenvalue of Ik, then eigenvalues of K are pure imaginary. So this is what we get from this result, that if K is Hermitian, then Ik will be, if K is skew Hermitian, then Ik will be Hermitian. Let us check this. In this example, the given matrix is skew Hermitian, its eigenvalues are I and minus I. Therefore, this skew Hermitian matrix A has pure imaginary eigenvalues. Now we were talking about skew Hermitian matrices and Hermitian matrices. We are talking about their eigenvalues. Hermitian matrices have real eigenvalues, while skew Hermitian matrices have pure eigenvalues, purely imaginary eigenvalues. Now we will talk about orthogonal matrices, and we see that an orthogonal matrix has eigenvalues 1 or minus 1. So let us try to prove this result. It has been given that A is orthogonal matrix. Then from the definition of orthogonal matrices, we know that A transpose is identity, or A transpose is nothing but its inverse, A inverse. So let us say lambda is an eigenvalue of this matrix A, then Ax is equal to lambda x, and also A inverse y is equal to 1 upon lambda times y, and that means A transpose and A have same eigenvalues, and that means lambda is equal to 1 upon lambda, or lambda square is equal to 1, and that gives me lambda is equal to plus minus 1. So if A is orthogonal matrix, then its eigenvalues are 1 or minus 1. So let us see how they look like on this plane. If I have a real axis here and imaginary axis here, then all the eigenvalues of symmetric matrices, of real symmetric matrices, will lie on the real axis, and the eigenvalues of skew symmetric matrices will lie on the imaginary axis, while this is a unit circle, and then all the eigenvalues of orthogonal matrices will lie on this unit circle. Now we come to similar matrices. Let A and B be two square matrices of order n, then A is said to be similar to matrix B if there exists an invertible matrix P of order n such that A can be represented as P inverse BP. The following elementary properties can be easily established with respect to similar matrices. The first is that A is similar to A. So if A is similar to A means there should exist some matrix P such that A is represented as A times, such that A is P inverse AP. So in this case, if we take P inverse as equal to identity, which is the same as P, then we can prove easily that A is similar to A. Secondly, if B is similar to A, then A is similar to B. This can be very easily established, and on the basis of this one can say the matrices A and B are similar. You don't have to say B is similar to A or A is similar to B, we can simply say that the matrices A and B are similar. Thirdly, if A is similar to B and B is similar to a third matrix C, then A is similar to C. Now one can see that the first property is reflexive property, second is symmetric, and third is transitive, and on this basis one can say that the relationship, that is similar, A is similar to B, is an equivalence relation. And one can also see that the identity matrix of order n, that is In, is similar to itself, because in that case P is I itself. Now if the matrices A and B are similar, then we can prove that determinant of A is equal to the determinant of B, or we can say similar matrices have same determinants. Not only this, but the trace of A and the trace of B are also equal. Further, if AM is similar to BM, if A and B are similar, then AM and BM will also be similar for any positive integer m. And finally, if A is similar to B and if A is invertible, then A inverse is similar to B inverse. These are some of the properties of similar matrices. Let us prove them one by one. So, to prove the first property, let us say A and B are similar, then this statement means that there exists a matrix P which is non-singular such that A is equal to P inverse BP, and from here we can get the determinant from both the sides. We can get the determinant of both the sides. So, determinant A is equal to determinant of P inverse BP, and we know the property of determinants, that this determinant of product is equal to product of determinants. So, determinant P inverse BP is equal to determinant P inverse multiplied by determinant B into determinant P. Determinants happens to be real numbers, so they can be they can change the order, and that means we can bring this determinant P here. So, it is determinant P inverse into determinant P into determinant B, and one can combine these two. It is determinant P inverse P into determinant B, and this is nothing but determinant of I, which is 1. So, we can say determinant A is equal to determinant B. That is the first property which we have listed. The second is trace of A is equal to the trace of B. So, we can write down trace of A is equal to trace inverse trace of P inverse BP, because B is similar to A. So, there exists such B, there exists such P. So, to prove this result, we will use this result with respect to product and trace, where we have this earlier established that trace of AB is equal to trace of BA. So, we can write down this trace of P inverse BP as trace of first matrix into second matrix. So, this means trace of P into trace of P inverse B. So, order has been changed, and that means this can also be, and since this product is associative, so we can write trace of P into P inverse B, and P into P inverse is identity. So, identity into B is B itself. So, trace of A is equal to trace of B. So, second result is established. To prove the third result, let us consider A is equal to P inverse BP. We will prove this result by induction. So, let us see what happens to A square. So, if we write down, if we multiply A with A, then it is A square, which is equal to P inverse BP A, which is equal to P inverse BP into P inverse BP. I have written these, this is first A and this is second A. So, we multiply it. This is multiplication is associative, so you can change the brackets, and that is why I write down this product as P inverse B into P inverse into BP, and that gives me P inverse B, this is I and BP. So, it is P inverse B I BP, and then one can write down this product as P inverse B square P. So, there we have written A square is equal to P inverse B square P, and from the definition of similar matrices one can say that A square is similar to B square. So, now let us assume that AK minus 1 is similar to BK minus 1. Now, we write AK minus 1 as P inverse BK minus 1 into P, because they are similar matrices, and then AK is written as AK minus 1 into A. So, AK minus 1 is this which is given to us, and A is similar to B. So, I write it as P inverse BP. If you simplify, then this expression comes out to be P inverse BKP, and that proves that AK is similar to BK. So, by induction this result is true for any value of positive M. That proves the result. Then the according to fourth property, if A is similar to B, then B can be written as P inverse AP. It is given that A is invertible. So, determinant A is not 0, that is what we have proved earlier, and that means determinant of B is equal to determinant of P inverse AP, which is equal to determinant of A. Since determinant B is not 0, so B is also invertible. once B is invertible, then we consider A into A inverse. A is similar to B, so I write it as P inverse BP into A inverse. Now A into A inverse is identity, so this is simplified to P inverse BP A inverse, or we can write it as P into I. If I pre-multiply this expression by P, so it is P into I is equal to P times P inverse BP A inverse, or left from here we can get AK as AK minus 1 into A, which is equal to AK minus 1 is replaced by this P minus 1 BK minus 1 P into P inverse BP, and if you simplify this expression, this comes out to P inverse BKP, and this proves that AK is similar to BK. Now by induction the result is true for M positive. Now to prove the fourth result, if A is similar to B, then B is expressed as P inverse AP. It is given that A is invertible, that means determinant A is not 0. Then determinant of B and determinant of A are equal. So determinant B is equal to determinant P inverse AP, which is determinant A, and this means determinant B is not 0, and that means B is invertible also. Then A times A inverse is equal to, A is similar to this expression, A is similar to B, so we write down A as P inverse BP multiplied by A inverse. Now this is nothing but identity on the left hand side, and then P inverse, we rearrange this term, P inverse is taken out, BP A inverse, and that means if I multiply this by P, then Pi is equal to P into P inverse into BP A inverse, and that means P is equal to BP A inverse, or B inverse P is equal to P A inverse from here, and finally P inverse B inverse P is equal to A inverse, and that means A inverse is similar to B inverse. So this is what we have to prove in the fourth property, that A inverse and B inverse are similar. Now these properties are helpful in checking whether A and B are similar. Like if I have been given these two by two simple matrices, then one can very easily check that they are similar or not. We can first calculate the trace of this matrix A, it is 4, and trace of B is 4, but this result is not conclusive. So we check the determinant. Determinant of A is 3 plus 2 and determinant of B is 4 minus 2. So determinant A is not equal to determinant B, although trace A is equal to trace B, and this proves that the two matrices are not similar. In this example, I have been given 3 by 3 matrices. Trace A is not equal to trace B. Let us check. Trace A is 2 plus 1 plus 1, the sum of diagonal elements, it is 4, and trace B is sum of diagonal elements as 3. So trace A and trace B are not equal, and one can conclude that the matrices are not similar. In this example, I have been given 2 by 2 matrices. Their trace 2 and 2 4 and 2 and 2 4. So trace A is equal to trace B. One can calculate their determinants. This determinant is 4 and this determinant is 4. So their determinants are equal. Can we conclude that A and B are similar? So my claim is that these two matrices are not similar, although their determinants and traces are equal. Now to show this result, let me have a square matrix P, which is taken a general matrix consisting of elements A, B, C, D, such that one can express A in terms of the matrix B as P inverse BP. So let us say there exists some P for which this is possible. So if we can find out A, B, C, D in such a manner, making P invertible, then we say that A and B are similar. If we cannot, then of course A and B will not be similar. So to do this, we write down A is equal to P inverse BP, or this can be simplified to PA is equal to BP. So, we first calculate what is PA. I have assumed P as ABCD and A is given to me as this. So, let us multiply them. So, it is 2A plus B and 2B, and this multiplication will give me this row, and PA is this 2 by 2 matrix. Similarly, I calculate BP. So, B is given to me as this matrix and ABCD I have assumed as this. Get this product, and this product comes out to be this. So, if A and B are similar, then PA should be equal to BP as I have shown here. So, let us try to show that this matrix is equal to this matrix. So, we have 2A plus B into 2A plus B 2B, 2C plus D 2D is equal to 2A 2B 2C 2D. So, if these are equal element wise, then the result is proved. So, this gives me 4 equations. 2A plus B is equal to 2A, this means 2B is equal to 2B, this means 2C plus D is equal to 2C, and this means 2D is equal to 2D. So, these are 4 equations. Since from here these are identically satisfied, but from here and from this one can show that D is equal to 0 and B is equal to 0. That means the matrix P will be of the form A C 0 0, and that simply means that determinant of P, whatever be the values of A and C, will be 0, and that proves that P is not invertible for any combination of A and C. And that means we cannot find a matrix P which is invertible such that A can be expressed as P inverse BP, or finally we can say that A cannot be similar to B. So, in this example we have proved that two matrices which have same determinant, same trace, but still they cannot be similar. So, it is not conclusive that determinant A is equal to determinant B, trace A is equal to trace B, then the matrices will be similar. Now, similar matrices share many other properties. We have seen that they have same trace and determinants. Now, I will show that they have same eigenvalues. So, let us have this theorem. Let A and B be two similar matrices, and if lambda is an eigenvalue of A, then lambda is also an eigenvalue of B. So, to prove this result, it has been given to us that A and B are similar. So, we can say that there exists non-singular matrix P, so that A is equal to P inverse BP by the definition of similar matrices. Let lambda be an eigenvalue of A. That means there are non-zero vectors x such that Ax is equal to lambda x. So, its characteristic equation will be lambda I minus A into x is equal to 0, and lambda I minus A, let us say it has the matrix A has eigenvalues lambda 1, lambda 2, lambda n, then lambda I minus A is equal to lambda minus lambda 1, lambda minus lambda 2 into lambda minus lambda n equal to 0, because we have assumed that lambda 1, lambda 2, lambda n are the roots of this characteristic equation. Now, since A and B are similar, so we can say P inverse BPX is equal to lambda x. So, I have written the value of A in this equation, and this gives me lambda I minus P inverse BP is equal to lambda P inverse IP minus P inverse BP is equal to 0. So, this lambda I have written in this manner. So, lambda P inverse IP minus P inverse BP equal to 0, and that gives me that P inverse lambda I minus BP, its determinant, equal to 0, and this simply means the determinant of P inverse into determinant of lambda I minus B into determinant of P, and that gives me determinant of lambda I minus B. So, I have started with lambda I minus A, and this comes out to be determinant of lambda I minus B, and that means the characteristic equation for A and for B, they are same. So we can write down determinant of lambda I minus B as lambda minus lambda 1, lambda minus lambda 2 into lambda minus lambda n. And since lambda 1, lambda 2, lambda n are the roots of this characteristic equation, lambda I minus A equal to 0, that means they are roots of this equation determinant lambda I minus B also, and that means the characteristic polynomial of A and B are same, and therefore the eigenvalues of A and B are also same. So that proves the result, and this means that if lambda is an eigenvalue of A, then it is also an eigenvalue for B. Now, although the eigenvalues of similar matrices are same, their eigenvectors corresponding to given eigenvalues may be different. So this is an observation that eigenvalues may be same. We have proved in the form of a theorem that eigenvalues of similar matrices are same, but their eigenvectors need not be the same. In fact, we say that similar matrices can be thought of as describing same linear transformation but with respect to different bases. Let me illustrate this with this diagram. Let us say we have a linear transformation, in fact linear operator from V to V. V may be Rn. Then any vector x under this operator will map to Lx. Let us say x as, let us say there are two bases for V, the S and T. So xs denotes the coordinates of this vector x with respect to basis S, and xs, so this is Lx, x will map to Lx. So Lx with respect to basis S can be written as B times xs. So this vector xs will map to this vector L of xs. So B is the transformation matrix. So xs is written as B times xs. Now this vector, the coordinates of this vector x in S is xs, but with respect to y, the relationship between, with respect to the another basis t, the relationship will be xs is equal to p times xt. So this is a transformation matrix which takes the vectors of, which takes the vectors coordinates xs to xt. So this vector when maps to this, it is p of xt is a times a of pxt, and then you can again come back from here, you can come back to this. So a transformation P inverse is to be applied, a matrix P inverse is to be multiplied to get this matrix. So that means it is BP is P inverse APXT. So we can say it is the same vector but in a different basis. Now we consider an example in which T is a transformation from R2 to R2 defined by this transformation. We have to find the matrix representation for the transformation related with the standard basis, and then we will also find the matrix with respect to the basis 2, 1 and 1, 1, and we will show that the two matrices are similar. This will illustrate what we have discussed just now in a diagrammatical representation. So we start with the vector 1, 0 and 0, 1 as the base vector in the standard basis. So 1, 0 will map to 1, 3 under this transformation. One can check x1 is equal to 1 and x2 is equal to 0. So this comes out to be 1, and the second element will map to 3. Similarly, T01 will be 6, 0. Then the vector 1, 3 will be represented as a linear combination of the base vectors 1, 0 and 0, 1. That means alpha is equal to 1 and beta is equal to 3. So these are the coordinates of this vector. Similarly, 6, 4 will be represented as alpha times 1, 0 plus beta times 0, 1, and that gives me alpha is equal to 6 and beta is equal to 4. Now matrix of transformation with respect to standard basis will now be written as 1, 3, 6 and 4. So, this was the first column vector and this is the second column vector which we have obtained earlier, and accordingly if we consider the second basis as 2 minus 1 and 1 1, then the transformation y is equal to Ax will give me t is equal to 2 minus 1 is equal to this matrix A and then 2 minus 1, and this gives me 2 and minus 6 is 4, 3 into 4 multiplied by 2 minus 1 gives me 2. So, T201 will become 4 minus 2. Similarly, T11 can be expressed as this matrix A multiplied by 1 1 and that gives me 7 7. So, representation of minus 4 2 and 7 7 with respect to second basis comes out to be a linear combination of this. So, minus 4 comma 2 is equal to alpha times the base vector 2 minus 1 plus beta times 1 comma 1, and then one can simplify this equation. So, it is 2 alpha plus beta is equal to minus 4 and minus alpha plus beta is equal to 2. So, when you solve these two equations, the coefficient alpha comes out to be minus 2 and beta comes out to be 0. Similarly, if you write down 7 7 as a linear combination of base vectors, then again we will have system of equations 2 alpha plus beta is equal to 7, minus alpha plus beta is equal to 7, solve them, we will get alpha is equal to 0 and beta is equal to 7, and that means the matrix with respect to second basis comes out to be minus 2 0 and 0 7. So, we have now we have two different matrices with respect to two different bases, and one can note that determinant A is equal to determinant B and trace A is equal to trace B for these two matrices. Now, the two matrices A and B may be similar. So, simply that these two results will not mean that A and B will be similar. We can say that A and B may be similar. Now, for this let us consider there exists a non-singular transformation P which is A B C D, so that we can write down A is equal to P inverse B P and then P A is equal to B P, and from here we can get A B into the first matrix is equal to second matrix multiplied by P, and from here if you simplify we will have left hand side as A plus 3B, 6A plus 2B, 6C plus 3D and 6C plus 4D, while on the right hand side we will have minus 2A, minus 2B, 7C and 7D, and from here if you solve for A and B, then we will have A plus 3B is equal to minus 2A, 6A plus 4B is equal to minus 2B, C plus 3D is equal to 7C, and lastly 6C plus 4D is equal to 7D, and from here one can get that 3 times A plus B is equal to 0 from these two equations, and that means if you solve these 4 equations in 4 unknowns, we will get A is equal to 1, B is equal to minus 1, C is 1 and D is equal to 2. This is one such combination, and since determinant P is not 0, that means P is non-singular, so inverse exists. So, we can say that A and B are similar because we could able to find out such a matrix A B C D which is non-singular and which gives us A is equal to P inverse B P. So, one can notice from this system that the matrix B is a diagonal matrix. Now, on the basis of this we can say that it is easy to find the inverse, determinant and eigenvalues for a diagonal matrix, because if it is a diagonal matrix the determinant will be simply product, eigenvalue then diagonal elements are the eigenvalues. So, and the inverse will be simply the inverse of diagonal elements. So, if the matrix happens to be a diagonal matrix, then number of things can be simplified. So algebra will be simpler if we can perform operations on a diagonal matrix similar to the given matrix. So that is how we say that finding a similar matrix which is a diagonal matrix will simplify the algebra. So finding a diagonal matrix similar to given matrix is discussed in the next lecture on diagonalization. So with this remark I close this lecture, and to summarize what I have done in this lecture, I have given the basic concepts needed for diagonalization. I have discussed eigenvalues of real symmetric matrices and similar matrices, and with this we are ready to discuss the diagonalization. That will be the content of my next lecture. Thank you.
Thank you.